Okay, I'm going to begin this review of the midterm with a discussion of limits. And there are two types of limits that we want to talk about. The first type is the limit as x approaches c of f of x, where c is some constant value there. And we say that a limit exists as x approaches c if the y values of the function f of x approach the same value from both the left and the right. And in terms of notation, this would look something like this. We would say that the limit as x approaches c of f of x implies that the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. So in order for the limit to exist, the two one-sided limits, the left side limit and the right side limit, must both exist, and they must both equal the same value. So that's the notation in a nutshell, that when the function approaches the same y value from the left as it does from the right, then the limit will exist for that particular x value. Now some notes. In most cases, the value of the limit at a certain point and the value of the function are the same. When this happens, we say that the function is continuous at that point. So for example, in the first diagram at the bottom, you have the function as x approaches some constant value c from both the left and the right. The y values are headed for the same point there. And if the function is called f of x, then the value of the function at that point is f of c. So we would say that the limit as x approaches c of f of x would be equal to f of c in this case. So this is the typical case. In any continuous function, the limit and the value of the function are always equal to each other. The second case, a limit may exist even when a function is not defined for a particular x value. So in the second diagram, you can see that as x is approaching c, both from the left and the right, the y values seem to be converging at the same value for the same value. And even though the function is not defined at that value, we would say that the value of the limit is equal to whatever the value is that it's approaching at that point. So in that case, the function is not defined at that point, but the limit does exist because the function appears to be headed for the same value from both the left and the right for that x value. For the third example, it says that a function may be defined for a particular x value, but the limit does not exist there. So in the third diagram, we see that the function has a value when x is equal to c. That's the shaded in circle there. However, as you approach from the left, your y is heading for a different value than when we approach c from the right. And that is what we call a jump discontinuity. So this is an example of where the function is defined for a particular x value, but the limit does not exist there. And the fourth example, or the fourth note, a function may be defined for a particular x value, and the limit may exist at that point, but the value of the function and the limit are not the same. Okay, so in the fourth diagram, we have this function of x, and we can see that it has a point discontinuity at x equals c. There is no value where you expect the function to be headed, but there is a value at a place higher up along the graph. And so the function is defined and the limit exists. The limit would be the value where the open circle is, and the value of the function is where the closed circle is, higher up. These two don't have to equal each other, and yet the limit can exist at that point. So this is the first video on limits, and we'll continue with more limits in the next.